Okay, in this video I'm going to do problem number 7 from homework 5 as an example. And in problem 7 we start off with a TDM frame structure problem. And it says, suggest a TDM frame structure that is an interleaving sequence for the case of 3 signals being multiplexed together, A, B, and C, with data rates 1 kilobit per second, 2 kilobits per second, and 3 kilobits per second respectively. And then parts B, C, and D ask us to go ahead and create frames with overhead, assuming various different combinations of bit or byte interleaving versus a framing bit or a framing byte. Okay, and for each of those cases it asks us to calculate bit rate and the frame rate. Okay, so I'll do that, and I'm going to start off by drawing a picture of our multiplexed bit stream. So this is TDM frame structure. And I'm going to go ahead and draw a picture here that shows streams A, B, and C being multiplexed together into a single stream. Okay, and the data rate for A, RA, is the bit rate for data is 1 kilobit per second. The bit rate for B is 2 kilobits per second, and for C is 3 kilobits per second. Okay, and so as we multiplex these together, there's C, here's B. We know that, for example, in signal A, we have the time for one bit, the bit period, is 1 over the bit rate, which is 1 over 1,000, or 1 millisecond. So 1,000 bits per second, 1 millisecond per bit. And in this, because this is a synchronous system, what we're going to do is every time we get a bit from A, we're going to get 2 bits from B because it's got twice the bit rate, and 3 bits from C. In other words, we can go ahead and create a structure where we have 1 from A, 2 from B, and 3 from C, all in the same period of time of 1 millisecond. Okay, so these are bits from A, B, and C. And so a natural frame structure would be something like A, B, B, C, 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 something like that. Okay, but this is an idealized frame structure, and in the real world we have to add some overhead, some framing bits or framing bytes to this. Sorry if it was crooked there. And so that's part A, and so in part B we're going to assume that we have byte interleaving, and that we have 1 framing bit per frame. 1 framing bit per frame. Okay, and so our frame is going to then look something like this. Here's that framing bit, and then we're going to have 6 bytes. 1 from A, 2 from B, and 3 from C. Okay, so this is going to be A, B, B, C, 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 and this is going to be my framing bit. And so the total length of this frame is going to be 1 plus 6 times 8, or 49 bits. And this frame has to be sent out in the amount of time. The time for a frame is equal to the time it takes signal A to send 1 byte, or for the time it takes signal B to send 2 bytes, or the time it takes signal C to send 3 bytes. These are all the same amount of time, and it takes signal A 1 millisecond to send a bit, therefore it takes signal A 8 milliseconds to send 1 byte, so 8 milliseconds. And so we can calculate the bit rate and the frame rate here. If this is the time for one frame, then the frame rate, R frame, is equal to 1 over that, which is 1 over 8 times 10 to the minus 3. And the frame rate comes out to be, let's see, where's my calculation, 125 frames per second. And the bit rate of the multiplex signal then is, well, it's going to be approximately 6 kilobits per second. If there were no overhead, it would be 6 kilobits per second. Let's do the calculation. It's going to be 49 bits in 8 milliseconds, or 49 divided by 8 times 10 to the minus 3, or 49,000 divided by 8, which turns out to be 6125 bits per second, or just a little bit above 6 kilobits per second, 6.125 kilobits per second. Okay, for part C, I guess I'll go to the next one. We're going to use byte interleaving, and we're going to use a whole byte for framing. So we're going to have a framing byte here, and then we're going to have an A, 2 B's, and 3 C's again. Okay, and so our frame is going to be 7 times 8, or 56 bits. And now it's easy because, let's see, the time for this frame is equal to the time for the other one because this is byte interleaving. We're sending a single byte from A. It's 8 milliseconds again. And so the bit rate is 56 bits per 8 milliseconds. And this comes out to be 7 kilobits per second. That makes sense. We're sending 7 bytes instead of 6. Okay, so instead of getting 6 kilobits per second, we're getting 7 kilobits per second. And the frame rate is 1 over the frame time, and it's 1 over 8 times 10 to the minus 3 again, or 125 frames per second. Just like in part B, 125 frames per second. We have the same frame rate. Finally, in part D, it's a little bit different. We're going to do bit interleaving. And then we're going to have one framing bit. Okay, so this is byte interleaving for part C, and one framing byte per frame. And now we're going to do bit interleaving, and we're going to do one frame bit per frame. And so our picture looks much the same, except, now I'll draw them, I guess, a little bit taller and skinnier. We're going to have a bit from A, 2 bits from C, 3 bits from C, and 1 framing bit. Okay, and so this is now 7 bits, and the time for a frame, so this is the length of the frame, and okay, so I can write LF up here for that one, and LF up here for that one. The time for a frame is the time it takes for 1 bit from A, T of what we called TA before, and that's 1 millisecond. And so our bit rate is 7 bits per 1 millisecond, which is 7 kilobits per second, just like part C. Why is that? Because we're adding exactly the same amount of overhead. 1 part in 7 is overhead. Here it was 1 byte out of 7 bytes. Here's 1 bit out of 7 bits. Finally, the frame rate is going to be 1 over the frame period, and that's 1 over 1 millisecond, or 1,000 frames per second. Okay, so that's problem 7. Hope that helps. Thanks.